compounds. Okay, so we're going to talk about the rule of thumb in about 2 slides. Okay, so hold off on that question for a minute. Somebody at this table had a question?
I couldn't find the answer number 11.
Number 11. What can you tell about the compounds ending in ate or ite? Okay, we're going to get to that in a second. We have to use that afterwards, yes?
I didn't know, like on number 15, it was like a blank.
It was a blank? The rule for naming bases?
Yeah.
Okay, the rule for naming bases, and I will just go ahead and spell out one off the bat because it's not one we're going to talk about like right up front today, is you always end a base with the name hydroxide. So it's like the base name, you put the metal first, whatever the metal's name is, and you say blank hydroxide. So like sodium hydroxide, potassium hydroxide, lithium hydroxide, beryllium hydroxide, blah blah hydroxide. So that's one of the names that we'll learn a bit more about today. Another question from reading guide 9. Blank spaces you guys have? For right now, you haven't had it?
The stop system, the classical system.
Okay, I'm going to go through that as well today. So I actually want you to hold your reading guides because there are a couple things on there that you've already written down that you can add to or you can elaborate on, because once you've already gotten your base understanding, when you add to it, it helps build your like connects the dots in your head. And I saw this TED Ed video the other day on practice. Thank you. On practice and how do you practice differently in like sports and then like in academics. So I thought I'd show it to you, but I'll show it to you a little bit later. Okay. Let's start with a couple keywords. Can you shut my door, Omar? Because I'm not quite sure what shenanigans are going on out there. Okay. Syrian, valence electron, what's up?
So the outer shell of electrons on an element.
Okay, so how do you know how many electrons or valence electrons an element has?
Based on its group.
Based on group number. Okay, so basically outer electrons, and it's the number that the group number is on the periodic table. What are the group numbers? What's the group number of nitrogen's group? 5. Okay, what's the number of oxygen's group? 6. Fluorine's group? 7. Okay, so that valence electron is just going to give us information about how many electrons it gains or loses to become an ion, if it were to become an ion. So that's important for in a couple minutes. Cations are what kind of charges? Positive. Anions are negative. Okay, you're making sure you're checking yourself as you go. What's the octet rule, John? Okay, so you're going to either gain or lose or share enough electrons to get 8 valence electrons in your outer shell, right? Okay, so what kind of compounds would commonly be losing or gaining electrons? Yeah. What kind of compounds? Yes, metals are in that compound, but what kind of compound? Go for it. Say again? Ionic compounds will be the ones that lose or gain, whereas covalent compounds will be the ones that share. Okay, so just kind of doing some quick reminders for us. What's an ion, Irie?
Is it whenever like the element loses or gains?
So it forms a what on itself? A positive or negative charge. Okay, I'm just going to say a charged particle, because that basically takes all what you said and puts it into a simple phrase. Frank, ionic is a combination of what types of atoms?
Metals and non-metals.
Right, so a metal and a non-metal get together to make an ionic compound. We're going to learn today that we're also going to have polyatomic ions that come into play as well. But I think that when you hear the word ion, what are you probably thinking? What kind of compounds is an ion going to take part in? Say again? So if I'm an ion, am I going to be in a covalent compound? I'm going to be in a ionic compound, right? You should hear the word there, okay? So that makes sense that these are an ionic compound. Covalent compounds are going to be consisting of what, Omar? Work with me here. You only got a couple of things on the periodic table. We got metals and non-metals in ionic. So what kind of things will come together to make covalent? Can you find in front of your table? Let's go. Metal, non-metal come together to make that. Okay, and then let's do a couple more here. Specifically on the periodic table, we know the general locations or the geography of it. Avery, where are the majority of the metals? Like, give me an element that I would look to the left of. So you say middle, so I know you're talking about like right here, right?
Yeah.
So what's the farthest over to the right that I would go to still be a metal? So zinc is a good ending of the transition metal, but there's a couple more. On your guys' blue periodic table, doesn't it have like a darkened line? Like on the zigzag right there? Okay, what's that line called? Or what's it supposed to indicate? The metalloid line. So there's supposed to be metalloids kind of on that horizontal or that diagonal. So if the metalloids are on that diagonal, and then to the left is mostly metals, to the right is mostly non-metals. Okay, so like germanium, gallium, tin, lead, those are all metals still, even though they're past the transition metals. Okay, so I think that's good. What are some patterns you saw or interesting things you saw? So let's go ahead and talk in groups about that on your interactives. If you didn't do the interactivities, you were listening like a boss. Talk about some of the things you saw in the names, specifically in the names.
So that when you put the compound together, you know, like oxide in the end.
Yes, it's very interesting.
Because there's like
Oh, that's like that oxide and the hydrogen. Oh, so you just said that.
All right, I'm going to get one interesting fact or pattern from each table. Let's start with Irie's table. Something you guys saw. Okay, so you saw some stock method with iron. So you saw like iron with a charge of 2 or 3. Okay, so a 2 plus and a 3 plus, and how was it denoted differently when you wrote the name? Okay, so iron 2 and iron 3. So it gave you numbers, which were Roman numerals, which we don't see all the time, but we only see sometimes. All right, so that's going to be a rule of thumb coming up soon. Avery's area?
We saw that all of them except one had oxygen.
Okay, so the oxygen mostly ended with the phrasing what? With the or suffix oxide. Okay, so we'll talk about the ides in a second. Kayla's area? They may have taken some of your thoughts, but anything? I'll come back to you guys. You're good. They may have a different thought or a different unique thing they saw. Those are probably the most 2 unique things. There's only a couple patterns you'll see, so don't get crazy on me. There's not a ton more you'll see. All right, so let's pause for a second. Send 2 people from your table to me now. Grab a little baggie. Grab one of these little baggies, and then grab a sheet. Here, there's a couple. Pass those that way. Grab one of these. Baggie, 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 baggie.
I'm sorry.
Avery. Irie, take one of these. So grab a baggie and like a little instruction sheet. There are more. All right, so let me have you guys go ahead and do this first because I think you guys are getting the point already. I like to guide you to understanding versus just tell you to memorize everything. So at your table, you'll be in groups of 2. So look at them now and claim them. If you have a 3Z, then either all 3 work together or split. The people, one person behind you is a 3. Okay. So I already cut the little cards out, so you guys are fine there. But you're going to organize them into categories based on their similarities and how their names are written and how their formulas are written. Okay, so 2 categories right now. Go. Do not mix the baggies up or I will haunt you in your dreams.
we need 2 bags. Okay, you need 2 bags. Why do you have 1? Like this one?
Yeah, we need to know.
Yeah.
Thank you.
Say again?
You need a category.
What in the world?
We have the
Similar. You're looking for patterns. You're looking for patterns.
Teamwork.
well, these are all I don't know.
Actually, I was thinking we could do it based on the prefix.
I was thinking we could do it based on
It was the prefix.
prefix.
That sounds good right there. Yeah.
So this is so that's 2.
Right. We're gonna have to. Here's A.
Oh, we split that.
So that's not gonna be together. Are we gonna put them in together? Oh wait, we can. We can.
No, we can.
Here we go.
Megan, we can't do that.
You gotta go ahead.
We could also base it on.
Wait, you wanna make sure if they have numbers or not? Yeah. Okay.
Don't they all have subscripts, guys?
No.
Yeah, they do.
They have one.
Technically, they're listed. If it's not there, it's assumed to be a what? Okay, so can you really categorize by subscripts?
Oh man. She just shot down my idea right there. It doesn't make sense. Yeah.
Oh wait, no. Look at the next step.
So we can only categorize.
Two even groups.
But I'm asking.
Don't you lie to yourself?
Yeah. Maybe when we these are like we could sulfur is like
I'm gonna bet some two,
Alright, pause, 5, 4, 3, 2,
yeah,
1. Okay, I see a couple groups have already started to make big categories. John, tell me what you guys did your big categories based on. So the ites and eights went together in a category, okay, and the IDEs, IDs go on in a separate category. So we're looking at the, Kaylin, we're looking at the suffixes. So that's kind of our big categories right now, ides and then eights and ites. So now further segregate them based on some other similarities you see within the category you made. So within your ide category, how could you make that into 2 groups? So I need to see that, and then we're going to discuss. So focus on one category at a time. Further, look for differences that you can categorize based on.
I do 8. Where's this stuff here? Where's this stuff here? I admit.
like if you have the eights right here.
Oh, is it deal with the eights of
The ites. I mean
it goes with what?
the ites.
Yeah, the primary molecular whatever.
Taking it further divided oxide.
Okay. How are we gonna break this down?
Wait, how do you break it down? How do you break this down? Because she said like after you have all the ites together, divide that into 2 separate. So where's and I was gonna say maybe we can divide it. Have the oxide and then have the other
Megan, these are all the same ones, buddy.
Yeah,
Yes, they are. I don't even.
How small do you want okay.
Raise your hand if you feel like you have a decent subgroup. You need some decent extra categories. Only taking the eyes. Oh, two. Yeah. Okay. All right, guys, let's look up here and let's let Bradley's group describe kind of how they started. And then let's adjust, and I'm going to critique you guys as you go a little bit. So listen up, okay? So I have all your compounds up here. You guys already split into 8s and 9s, and then ides. We're looking for commonality in our speaking of the language, right? That's where we're looking for patterns. Tell me how you guys further broke down your ides.
We broke down the ides by separating them into ones with oxygen on the end of it, and then ones without, because there were like half of them were ones with oxygen.
I had a number of groups say that. So, is the presence of oxygen the most stark difference you saw between how the names were? Because I think you guys were only looking at maybe the formula, like, oh, it's got oxygen or it doesn't. Because you have an oxygen doesn't mean that you're one compound type or another. It just means that you have oxygen in it. So, let's extend that thought. Frank.
What I did was I broke it up into the amount of atoms they had, like.
So some had a lot of atoms and some had a little.
So I broke it down to 7, 6, 5, 4, 3, or there's now 3, but 5, 4, 3.
So how are those numbers of atoms said in the formulas?
Like when you.
Or in the naming part?
For like CO2 is carbon dioxide.
Okay, so you're using a prefix to say the number of oxygens. Yeah. But what about like in this one? Oh, that's carbonate. Hold on, let me find one that doesn't have that. Why doesn't this one say, where does the zinc one go? Why doesn't that one say a prefix?
Because it doesn't have any like extra.
Well, that has one oxygen, right? You guys with me? Okay, but then I would go back up here, and this one has one oxygen, but it says monoxide. I'm throwing holes in your theory. Okay, so can someone else extend off of that? What makes the name so dang different? Yes, there's a prefix to indicate a number of atoms on some but not others. So let's look deeper. You guys just told me what made things ionic. What made things ionic? Okay, a positive thing and a negative thing, but what kind of atoms came together to make ionics? What kind of atoms? Types of atoms from the periodic table? Metals and nonmetals. So, is that ionic? No, because it has 2 nonmetals, okay? So I use the prefix there. And then, but is that ionic or covalent? Look for potassium. Ionic, so I'm not using prefixes, right? You don't see that. Okay, but then I see sulfur hexafluoride, ionic or covalent? Why covalent? 2 nonmetals. I should have more than 2 people with me. Okay, who's with me? Give me like a little, yeah, okay, thank you. So I see a sulfur and a fluorine, that's 2 nonmetals, that's covalent. So then I'm saying a hexafluoride, I'm saying a word with the number through the prefix. But then I see this one, calcium oxide, there's oxygen, right? But there's also a calcium, which is a metal. Okay, so you should be identifying the metals first. Do I have to use a prefix to describe it? No. And then I see magnesium nitride. Is that ionic or covalent? Ionic. Do you see prefixes in there? Okay, no. So what you're thinking now is, when do I use prefixes? Let me get some hands up. Who's figured it out? A couple of us. Caleb, when do I use prefixes? Beautiful. Say no more. You only use prefixes for covalent. If you don't write that down, you'll be hurting later. That point is horrible. Prefixes go with covalent, and that is a generalizable pattern. There are a couple that have some interesting other terms that go along. I'll call it prefix, but it's not truly one of our prefixes we look at. William.
So with like copper and transition else, stay small and ionic.
Yes, because if you're a metal, you're still ionic. So your eights and ites category you had, those are all ionic because they all started with copper, calcium. What else do we have that was eights and ites? Oh, ammonium is a positive ion. I'll get to that in a second. Iron, those are all metals, so those are all ionic, no matter if they ended in ide, ate, or ite, they were still ionic. Yes, sir.
So then how do you tell the difference between like nickel chloride up there
Mm-hmm.
that has a subscript of 2, but how do you tell the difference, like if you would just say that nickel chloride, like if you would think it's just 1?
So you have to say nickel 2, because I will tell you, we'll talk about charges a lot. The charges are what's going to tell me information about the formula. The charges are only going to go with ions, which only goes with what kind of compounds? Ionic. Ions, ionic. So we're starting to learn some patterns here, okay? So let's bounce back here. I think you guys saw the gist of that a little bit. Let me go here first, okay? So we're going to take a couple notes first, and we'll do some examples. Put your things back in your baggie. Put your things back in your baggie. Write down the information on the board, and then we'll kind of keep clarifying the observations you've already made. Thank you for not mixing those baggies up. Write down some notes. I want to see everybody writing down the examples from today, because this is the language we will speak forever. Oops, I'm sorry. All right, so when I say the word nomenclature, it just means naming things, writing formulas. So naming things and writing formulas, we have a series of ways that we indicate information through written formulas and written names. Of course, we have symbols, just straight up symbols, like the periodic table tells us all the atoms we have to work with. We know now the metals are on the left side, it's about 70% of the periodic table, the non-metals on the right side, so a very small part of the periodic table. And so if we just have a single symbol like this, we say an atom of sodium or an atom of chlorine. So we're trying to make sure we're using the terminology correctly so that I understand what you're saying and you understand what I'm saying. Now, as soon as we plop them together, we start putting other atoms with other atoms. We then start to say, oh, this is a formula. This is the chemical formula for that substance. And substance is a really generic term. So many times you'll hear me, instead of saying substance, I'll say the word compound. The compound is a pure, so it's going back to Unit 1, a pure substance that came in 2 varieties. Now that we know those categories, pure substances we knew or initially were just simply elements, or they were compounds. Well, here's our elements up here, just purely written as a symbol, and here's our compounds as we start to combine the atoms together. At this point, you should be okay with identifying if things are ionic or covalent. So I see sodium and I see chlorine. If you don't look at the periodic table now, look at it now. It's going to be hard for you to kind of make sure that you know your metals are and your non-metals are. There's a series of periodic tables around you. Sodium's on the mainly the left. Okay, so we have a metal here, and then chlorine's a non-metal, okay? So that is a what kind of compound? Ionic. We will go over that about 50 times today, okay? So if you have a metal and a non-metal together, it makes an ionic compound. The term we use to actually say I have an ionic compound is not always I have an ionic compound. That's one way of saying it. We'll also use the word, this is a formula unit of an ionic compound, versus saying the word molecule. Molecule is a very specific term. So if we have a formula unit, also known as FU, which is how I will probably abbreviate from here on out, we will call it an ionic compound. And you're visualizing metal, non-metal together. So then, does anyone know the name of this NaCl? NaCl. Sodium chloride. Sodium chloride. You already know some of you mentioned you've heard them before. Who knows the name of this one? Carbon dioxide. Okay. So, carbon dioxide, you've heard me say ide and ide on both of those. So the ides don't really give you a lot of information. Ides just say, hey, this thing's from the periodic table. That's about it. And it's binary. It means it has two elements involved, sodium and chlorine, and then carbon and oxide, or oxygen. So at this point, tell me, is this ionic or covalent? The CO2. That's covalent because it's nonmetal and nonmetal. So that's our covalent molecule. Where we had an ionic formula unit, we have a covalent molecule. So we're just learning the names that are, or the terminology that's associated if you're ionic or if you're covalent. So if I say molecule, you're visualizing what two things have come together. Two nonmetals have come together. Soon, we will be starting to write equations out like this to show that, hey, this chemical compound reacts with this chemical compound to make a new chemical compound. And we've seen this before already. What did we use for our chemical equations for? We used them to indicate a law. Right, law of conservation of matter or mass. And we used the coefficients in the front to show there were the same numbers on left and right. And over here we call the reactants, because the reactants have to react to make the products. So we've been writing chemical formulas out for a little while, but now we're actually going to learn how to say their names right. If you get sleepy on me on a Wednesday, please stand up at the loud station, because I don't want to squirt water at you, okay? All right, so I'm moving on. All right, so I think we mainly found this out. Give me a couple facts about ionic. Things that you would indicate to you that you have an ionic compound. Metal, non-metal, what else? Positives and negatives. No prefixes. I could say the word formula unit and you'd classify it there. What was the thing we were writing the Roman numerals? The charges of the ions, which are only for transition metals. Okay, so then everything opposite of that would be covalent. Okay, so here is, you guys said, oh, you guys didn't say this back. You said ions, classifying as ionic. There would be no ions in covalent. And then metals, if we see a metal, we're certainly going to say it's probably ionic. If we see a metal, it's not going to be covalent. If I see metals and nonmetals together, that's ionic. If I see only nonmetals, it's covalent. So you're still classifying them just based on some similarities throughout the formulas you already saw. These are the new ones. Polyatomic ion, I'll tell you, we eventually will get there, maybe 2 minutes or so. It's on the half sheet I gave you. There's a list of polyatomic ions. Can you say the word? Ion. Okay, so if you're an ion, you're still going to be ionic. Right. And I think, Ira, you told me what an ion was earlier. What does the word ion mean one more time? Charged. Yes, charged particle. So if you have a charge, you're like a +1 or -2 or anything like that, you have an ion. It's going to be in the ionic category. You will not have charges or ions or anything like that in a covalent substance. Instead, we don't use charges, we will use prefixes to indicate a number, whereas we'll use charges to indicate a number over here. We're getting there in a second. Okay, cool, and then Caleb got me here. Okay, feels good so far. No one else other than those couple people? Okay. All right, so those are our big categories. These are how we're identifying them based on the looks of their formulas. All right, so I'll just skip a couple of these. Some of these are not relevant. This one, do you need to write this down? Read that and tell me if you need to write that down. Is that obvious now? So SO3, first off, identify ionic or covalent. How do you guys know covalent? 2 nonmetals. Oops. Non-metals. All right, so 2 nonmetals is definitely covalent. Okay. How many sulfurs do I have in my formula? 1 sulfur. How many oxygens do I have? 3 oxygens. Okay. So as they come together, you could even draw the Lewis dot structure for it. You could draw, you count them up, there's 24 electrons. Yeah. And you draw your sulfur trioxide if you really wanted to. Like, you know a lot about that at this point. And then we don't call it a formula unit, we call it a molecule. And we can determine the molecular polarity and the molecular geometry and the intermolecular forces. We could determine a lot about that, so we've learned quite a bit at this point. So we know it's covalently bound, it shares electrons and so forth. So I think that you guys feel good about this. Am I assuming good, right? Okay. All right, so let's start talking about how to name these then, okay? So I'm gonna skip that for a second. We just did that. Wonderful. All right. So here's how we're gonna start writing ionic compound names. This is your set of instructions. I'm gonna demonstrate through this first example, and then we'll do a couple kind of back and forth between our groups and then with me. So if you're writing an ionic compound, I'm starting with ionic because it's the hardest. We want the most time with it. So you're probably seeing, get the symbol, so periodic table symbol, and the charge from the ion. So we are already assuming the ion has formed. It has either, what are two ways to make an ion? Yes, it has already gained or lost electrons to become, what's the perfect rule? Octet. It has already gained or lost electrons to become octet. Which I started, I'm almost done finished, almost done grading your problems at 7/8. And most of you guys did a really good job with the electron configurations of dropping off electrons or gaining electrons to get to octet. So I'm going to demonstrate that with you now. So we're assuming the ions have already formed. Occasionally we'll need to use the periodic table because you don't remember where things are, so you'll use that a lot. And occasionally we'll have to use our polyatomic ion sheet, which is in front of you, and we will have those memorized. So once we have our charges, we're going to write them down. So go ahead and write this example down with me. Sodium, and if I don't put a number, what is it? What do you assume it is? A 1, okay? And right next to it, chlorine, and I'm writing a 1 negative next to that. I'm not going to move any further until you give me the thumbs up. So those of you who are thumbs up, you're waiting on me. Remind me sodium, just sodium's electron configuration. 1s, 2, 2s, 2, 2p6, 3s1. Okay, so this is straight up sodium. How did I get from sodium to sodium 1 plus ion? I lost the entire last 3s energy level with that 1 electron, which made it a 1 plus charge. Do you remember that conversion? How do we get from there? Okay. Chlorine, just straight chlorine. 1s2, 2s2, 2p6, 3s2, 3p, just normally is 5, right? So if I look at this now, how many valence electrons does it have? Say again? 7, because there's 3s2 and 3p5, so there's 7 there. So what is it going to do to become stable? It's going to gain 1 electron where? In the outer shell to make 5 go to 6, which is where we get the chlorine ion here. Okay, so we already know a little bit of that information. All right, so after we know the ions form, we know they're going to come together, we actually have to take their charges, sodium 1 plus, chlorine 1 minus, and we're going to take the charges, drop the sign, but keep the number, and crisscross the charges to make subscripts. Okay, so we're crisscrossing charges to make subscripts, and the subscripts are the numbers at the bottom of the symbol. So it's pretty easy when you have ones, because a 1 crosses down and another 1 crosses down. So we can write it as Na1 Cl1, but that just looks stupid. So we usually drop the 1s as well, because if there's not a number written, you always assume it's a 1. So many times instead of writing Na1 Cl1, you will probably just have written NaCl, and understanding that there's 1 of each of them. So that makes sense. So I had 1 positive, 1 negative. I needed 1 of each to cancel each other out to make an electrically neutral substance. That's how we kind of remember our ion groups come together to make an equally positive, equally negative substance, make it neutral. So look at calcium in the periodic table. What group is calcium in? It's in group 2. It has 2 what? Valence electrons. It loses those 2 valence electrons. I'm not going to write the electron configuration out for everything. But when it loses those 2 valence electrons, it gives our positive 2 charge. Chlorine's still there, But how many chlorines would I need to cancel a 2+ charge? 2 of them. So normally when we draw a Lewis structure, you would draw 2 of those. You transfer those 2 electrons. It would make a 2+, 1 negative, 1 negative. So we'd have 2 of them like that to cancel the total charge. But instead of writing it out with numerous calciums and numerous chlorines all the time now, we actually can just assume that if we crisscross charges, the charges will negate each other. So I've taken my 2+ and I've threw it down here. So I have a 2 down here now. I took my 1- and I threw it down here. And there's a, what here? A 1 there. Okay, so this is called crisscrossing charges. And if you hear the word charge, you should be thinking ion. Yes?
So the -1 can't be -1 CA.
Yes, so good point. The sign is dropped. The positive and the negative sign is dropped because it would just look kind of crazy. At this point, when I write calcium chloride like that, CaCl, 2, I'm assuming there's a number 1 there, number 2 there, but you know that this has to be true because the calcium carries a charge of what? What's the charge of calcium? Ion. +2. So if that is grouped together with 1 chlorine ion, what's the overall charge of this going to be together? Say again? A +1, and I can't have that. A +2 and -1 charge, it's not gonna balance each other out. So you have to have 2 chlorines, both with a -1 charge, to cancel out that +2. So we know it's a 1-to-2 ratio. We knew that when we were drawing our Lewis dot structures. Now we start to write it out really quickly, but you still understand that there's still a calcium ion and 2 chlorine ions there together, even if you don't see the ion charges anymore. Do you still remember? You got to remember that's still there. Yeah, question? There's not a lot of exceptions. I'll show you how to reduce. That's about it. Okay, so we have to crisscross only for ionic compounds. All right, so let's go. Well, before I go to the more examples, there are a couple of trying to do some periodic table. We've seen this quite a bit. You know that if you have less than what electrons, you gain electrons. You lose electrons. Less than 4, which is carbon's group, you're going to lose electrons. So if I lose my 1 valence electron, what's my charge? +1. If I lose my 2 valence electrons, what's my charge? +2. If I lose my 3 valence electrons, what's my charge? +3. If I lose or gain 4, I'm either a plus or a -4. I will not give you any in this category as an ionic because that's too hard. You won't know which is which. But at 4, once I get past that, what am I going to start to do with electrons? Gain instead, because I'm already close to 8, right? I'm not going to lose like 7 electrons. That'd be a waste of time. So group 5 has how many valence electrons? It has 5. How many more does it need? 3. So if I gain 3 electrons, what's my charge? -3. And then group 6 has 6 valence electrons. It needs 2 more, so what's its charges? -2. Group 7 has 7 valence electrons. Needs 1 more. It gains 1. -1. Well, what happens to group 8? Nothing. They're already happy. Please don't change their electrons. Okay? That's what everybody's striving to be is octet. So there's a trend. If you're in group 1, 2, and 3, you're a +1, 2, 3. If you're in group 5, 6, and 7, you're a -3, -2, -1 charge. If you are forming what kind of compounds? Ionic. We're sticking with ionic for now. Give me a thumbs up if you get that now. Okay, I skipped the transition metals for now because I need you to see they're a little different. We're going to talk about the Roman numerals here in a second. All right, so I'm going to come to them in a second. Let's start with naming. Writing the formulas for 6, 7, and 8. This is on your sheet in front of you, okay? Stay engaged with me, Nazla. I think there's some good examples that you're going to want to make sure you write down. I don't have mine are not numbered on your sheet, but you are looking at the page that has lithium carbide on this little section right here. Turn it over, yeah. Over here. Alright, so you found the name. Alright, step 1 in writing the name, you write the symbol. Okay, let's look for lithium. What's the lithium symbol? Li. You're looking on the periodic table. Which group is it in? It's in the first group. Okay, guys. If I'm in the first group, what charge do I form? +1 because I lose 1 valence electron, so write your positive 1 up there. Second element, carbide, sounds like carbon, okay? So I will go ahead and tell you now, this is our carbon example. If this formed the positive charge, this has to form the negative because they have to offset each other. And so carbon's in group 4. You're looking at the periodic table because I know you've not memorized the periodic table because you don't need to. So group 4, it's going to form a 4 what charge? -4, 4 negative charge. So at this point, they are going to cancel each other out only if I have enough of each of them. But the way I make it work is when I crisscross it, I actually already automatically make equal the number I need to equalize it out. So when I crisscross this, what do I get? Li 4 C 1. And I don't have to write the 1, but I can. This is the formula for lithium carbide. Yeah.
So you don't have to put +1 either, right? You can just put plus.
Right, don't put the charges down here. Put them up here so I know that you know your charges, but then when you crisscross, drop the sign. Jacob, go stand at the lab station. Thank you. All right, so let's do another one. Beryllium. Find beryllium. Find beryllium. What's the symbol?
Be.
Be. Okay. Charge of beryllium. How do you know that, William? It's in group 2. It has 2 valence electrons. It loses 2 valence electrons. It has a 2+ charge. Okay. And then nitride sounds like nitrogen. So look at nitrogen periodic table. It's in group 5, so it has a -3 charge because it gains 3 electrons. I'm just repeating that for a while so you know your process in your head. Okay, 2 + 3 negative crisscross. What's your formula? B3 and 2. So when I start to see these numbers, you have to see that fact that it's ionic, and then you can uncrisscross the charges to verify the charges are correct. But those are just going to be said as beryllium nitride, and I know that 3 came from nitrogen and that 2 came from beryllium, but I require 3 berylliums and 2 nitrogens to make it overall neutral. Because 3 berylliums would have a total charge of what? 2 + 2 + 2 would be 6+, and 2 nitrogens would have a charge of 6-, so 3 negative, 3 negative. That makes it overall neutral. So that's why those numbers work out the way they do. Okay, one more. Aluminum. Find it. Aluminum's in group 3, and it has a 3+ charge because it loses those 3 electrons that it has. And fluoride sounds like fluorine. Okay, so it's in group 7. It has a 7 valence electron, so it gains 1 as a -1 charge. Okay, crisscross. What do you get? AlF3, and you can put Al1F3 or just not put the 1. Needs understood it's there. Okay, so that's how we yes.
I was gonna ask, like, is there a way to find the positive or negative charges when, like, we're given the formula?
Yep, I'll show you that when we get to the formulas to name them first. Okay.
Okay.
So that's how we write our simple ionics. These are called binary ionics, and I'll just make you write that word down so you don't forget what that means. Binary means 2, okay? And binary ionic means that there's 2 elements in the compound. Aluminum and fluorine, beryllium and nitrogen, lithium and carbon. Yes, there's a number of them. There's 4 of those, there's 3 of those, there's 3 of those, there's 2 of those, but there's just 2 types of elements. It's called binary ionic. Okay, so let's go, we're going to do some more binary ionics, but we're going to do with transition metals now. Okay, so the transition metals, you saw the periodic table, they don't have no standard charge, whereas everything else here and here had a standard charge. So there are a couple that you have to become very familiar with, but we always use the stock system or the classical system to indicate their charges. Write these down, and I'll tell you my little tricky ways of remembering these. Because some of them have like really regular charges they take on, like zinc and silver, but then tin has 2 options. Cobalt has 2 options, iron has 2 options, cadmium has 1 option. So zinc always will form a 2+ charge. And I always say a Z looks like a 2, right? Zinc, 2, okay? And then I'm not really a fan of gold, but silver's number 1 in my group, okay? Silver is number 1, it has a 1+ charge. always. Always. And then cadmium, I don't have a silly way for that one, sorry. Cadmium always gets a 2+ charge. And so you'll see zinc is here, silver is here, and cadmium's here. So these are the ones that always have a standard charge. So just like sodium has a standard charge and calcium has a standard charge, when I'm writing the name out, did I say the charge with the name? Did I earlier? Did I say sodium 1 chloride? No, I just said sodium chloride, calcium chloride. So if you always have a charge, you don't have to say the charge. It's understood. We all know what those charges are. Now, if you get any of these in the middle, you cannot assume that if Kaylin says to me, yeah, you know, 10 chloride, I'm like, 10 what? 10-2 or 10-4? Because now it's questioning. I don't know what the charges she's talking about. So she will say 10-2 chloride to indicate a 2+ charge, or 10-4 chloride to indicate a 4+ charge, or cobalt 2, or cobalt 3, or iron 2, or iron 3. We will say the name as a Roman numeral. And that's how we get across to each other, hey, this is this particular version of this transition metal. And I'll show you guys some more examples with this. So those are the couple that we'll kind of work with. But if you see anything else, like let's say I tell you nickel 2 chloride, you're hearing me, right? You're hearing me saying nickel 2. So I'm telling you the charge of nickel is 2+, because nickel's right, where's it at? I lost it. Right here. Like, it's in this random place in the periodic table. How do you know the charge? It doesn't have a standard charge. That's why we have to communicate a little differently with transition metals. So, oops, here it is. All right, so there's a number of them. There's a lot of variability in the transition metals, but we will always use a stock system. This is the one that will give us the most information. We'll get to the classical in a second. This will give us information about which charge are you talking about on that transition metal. Yes?
So is it always positive?
Yes, because metals, good point. Metals lose electrons 100%, right? They never would gain an electron. So they'll always become a positive charge of some sort. So this is only for transition metals. So if I say 10-2 chloride, the Roman numeral is telling you 10's charge. So what's 10's charge? 2+. Write that out as you write your example out. So Sn is what 10 symbol is. 2+ is its charge. Look at chlorine. What's chlorine's charge? Look at the periodic table for chlorine. -1. So if one gets a charge, the other one does too, because they're both ions. They must complete each other. Crisscross your charge and tell me the formula. SnCl2. So the way you say this name out is 10-2 chloride, because that 2 is indicating the charge of 10. So when I say 10-2 chloride, you're hearing this name, but you're seeing this formula. And then what's this Roman numeral? 4. So whose charge is that showing you? Lead. So write out lead 4 sulfide like you see here. And so when I say a letter or a number in the middle of a name, I'm telling you the metal's charge. So what's lead's symbol? Pb. And what's the charge of this lead? 4+. And lead comes in many varieties. I've told you a couple of others that have some variability. Copper usually is a 2 or 3, like you guys just wrote down. Iron's a, no, sorry. Copper is a 1 or a 2. Getting ahead of myself. Copper's a 1 or a 2. Iron's a 2 or 3. Mercury's a +1 or +2. Lead is a +2 or +4. Same with tin. Chromium's usually +3, but it can change. Manganese is a +2, 3, 4, 5, 6, 7. It has a lot of charges it can take on. So that's what I'm saying. There's a lot of variability. Ain't nobody got time to memorize all those. Trust me. You have to use the system. All right. So lead 4. What's sulfide symbol? S. Charge 2 negative because it's in group 6. Okay, so now when I crisscross these, what do I get? PB2S4. All right, so this is the point where you have to kind of take a minute and breathe and go, that's not the lowest ratio I could go. If you have a ratio that's an even number, you can always reduce it down to make it simpler. So this is an exam question. They had this 2 years ago in the exam. PB2S4, I can reduce the 2 and the 4 down to 1 and 2. So if I write the symbol, if I write the formula like PBS2, you have to, one, backtrack and go, all right, seemingly lead has a what charge in the formula in black right there? No. If you take that lead, PBS2, and you crisscross it back up, it looks like lead has a 2 charge, right? It looks like sulfur has a what? -1. And then you go, not sure about that. Look at sulfur. Heck no, sulfur can never have a -1 charge, ever, because it's in group 6, so it gains 2 electrons. So you have to know that's fishy. So probably this is not correct the way that you uncrisscross the charges. You have to then see, oh, that was half, so let me double that charge back. So this was half, so it was a 4. And that helps you see from the formula back to the name how the name is not what it seems on here. There's only a couple of exceptions like that. Okay, so the last part about transition metals is your classical system here, which we don't see, we see like 2% of the time, but I'm just going to let you know. It has a Latin root to it. So all the symbols that have some funky, like Fe. How does Fe mean iron? Like iron, Fe. There's not even similar letters there, right? Well, it's because in back in the day, they called it ferrous or ferric. So the fer, that's Fe. That's where they got the symbol for iron. So if I say something is ferrous or ferric chloride, I'm referring to the Latin root of iron and chlorine, but it's your job, based on this little ending that's different, is to determine which charge it is. So go back to your notes you just wrote down for iron. What were the 2 charges that were optional for iron? 2 and 3, okay? So because you know 2 and 3 are my options, the os is the low. Os is the low one. Ik is the high one. I have to make up stupid things to help you guys, okay? So os is the low, ik is the high of the charges that we had as our options. So Ishmael, what were the charge options again? 2 and 3. So ferrous would be the lower charge, which is 2+, and then ferric would be the higher one, which would be 3+. And then what's our charges always for chlorine? It's in group 7, so it has a -1 charge. So how these formulas differ? Iron, chlorine, 2, and then iron, chlorine, and 3. So when you see these formulas, you name them. You can either say iron 2 chloride or ferrous chloride, or iron 3 chloride or ferric chloride. All right, I'm sure you're feeling overwhelmed right now. I think you need some examples to practice. So go to the ones, oops, we just skipped. Go to the number 9, so chromium 3 oxide, and then 13 and 14. Try those out right now, the people in front of you. I'm going to come around. So the ones in yellow, so number 9, 13, 14. I'm sorry, they're not numbered on your paper. The ones with the transition metals, basically.
It's 24.
guys should be talking to each other. Talk to each other.
Wait, oxide.
Oh,
I was gonna say, wait.
so it'll be
CR.
Oh, yeah.
CR2. Wait, because oxygen is group 6, so you have 2. So CR2, CO3. Oh, no, it is. Wait. Which one? Oh, I was right. We're doing the chloride one, not the oxide. You're doing that too. Oh, no.
If that's the case, you're right. We're 13, but that's not 9.
So, that's minus 1. So, chromium chloride would be CrCO3. And then lead would be Pc. With 2 positive charges. That'll be 3, 4, 3 negative.
Okay, 10 more seconds there, and I want to go over those 3 with you. Alright, back up here for me. I think, if it's ionic, you have to find the charge. So I went ahead and wrote my charges up here. Where'd I get my 3 plus for chromium? From the Roman numeral. Where'd I get my 2 negative for oxygen? It's in group 6, it gains 2 electrons. Okay, so starting with that one, as you crisscross your charges, what do you guys get? Cr2O3. Okay, that is the formula for chromium 3 oxide. We say that differently than our other ones because they have a transition metal with a variable charge. Chromium 3 again, chlorine has a -1 charge. Crisscross, what do you get? Cl3, good. So if you see that name, you see chromium, you see, oh, it's a transition metal. When you say that name out loud, you have to say the transition metal's charge. Chromium 3 oxide. Chloride. And then lastly, lead has a 2 charge because of the formula here. Phosphorus is what phosphide is indicating. It's in group 5. So you jump 3 over to get a -3 charge. So then as you crisscross, you get Pb3, P2. So it looks like we're just jumbling letters together, but we have a process. You have to find charges, you have to crisscross charges. That's the basic part of it. Any questions on the transitions right now? I'm trying to do at least 3 examples of everything, okay? So first ones we did we have transition metals? The first style? No, we took the name, we took the symbol, crisscross, we're done. Okay, then we did some with transition metals, which were still binary because it's still one element with one other element. Now we're going to do some that are ternary, meaning they're bigger. They have they have different endings. They have a polyatomic ion and so forth. So, let me show you these first, okay? So on the back of your half sheet, it has your polyatomic ions. Look for the trend that you see in how the names are written. What are some commonalities between them? What are some commonalities you're seeing? Okay, first of all, they're all ions because they're polyatomic ions. They have a lot of 8s and a lot of ites. Okay, so mostly 8s and ites are going to be telling me, hey, I have a polyatomic ion. I can't just pull the information off the periodic table. I have to know it, or right now you're going to be using this sheet. What else do you see on there? Yeah, see, I hate that we have ides on the polyatomic ions. You see the hydroxide and the cyanide. Most of the time, ides, IDE, comes right after the periodic table, like hydride, nitride, oxide, chloride, bromide, sulfide, phosphide, blah, 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 blah. So ides, because I'd rather use the periodic table, right? Because I don't have to memorize anything, I just know how to use it. So most of the time, 95% of the time, ides are from the periodic table. That symbol, that element. Except for when we see hydroxide and cyanide. Those are 2 polyatomic ions that we'll see here. So let me give you some tips that kind of help you understand what you actually need to memorize and what you actually kind of can get from your rules. So guys, tell me chlorate. Formula for chlorate. ClO3 -1. Okay. Tell me for chlorite. ClO2 1-. What do you notice? Okay, so as you drop from 8 to ite, you drop an oxygen. You might want to write down this example. I'm going to do maybe one or two to show you the trend you should see, okay? So as you go from, if you go from the name system, the same ion, but you change it from 8 to ite, you drop an oxygen. The sign stays the same, the format stays the same, and all that jazz. All right, if you want to write down another example, here we go. Somebody tell me phosphate. Phosphate. P, look on your sheet. PO4, 3 -, okay? Tell me, is phosphite on there? Well, then you can tell me, using your rule, if phosphate is PO4, 3 -, what's phosphite? PO3, still 3 -. Okay? Again, tell me nitrate. Nitrate. NO3 -1. Okay? But don't even look at your paper. What's nitrite's formula? Oops. Nitrite is NO2 1-. Check your sheet. This should be right. So there's this trend of, if you know the 8 version of it, you already know the ite, because it's just 1 oxygen less. Okay? So you're dropping an oxygen on all these examples. So, but you see some other variations, right? So what are some other things you're seeing on there that's not an 8 or an ite? It could even be a prefix. Say again? There's a thiosulfate, there's a bisulfate, or there's a perchlorate. You see perchlorate? You see the hypochlorite? There's a lot of new little prefixes that come and go. They're not as regular as these. This is the most regular thing you'll see. But I will go ahead and tell you the other systems, just so whenever you get there and you're starting to make sense of them, you have something kind of, that tangible item put on there. So everybody write on your chlorate, chloride example, put hypochlorite right underneath your chlorite. And then who's ever heard of the prefix hypo? Where have you heard it, Meredith? Hypotonic solution, okay. So hypotonic solution means your cell swells, okay. It's because there's a lower concentration of like salt as compared to the water. So lower. Who's heard? What are those needles that go under your skin? Okay, I was really hoping no one would know that. Hypodermic needles. So hypo means below. Hypo means low. So if I'm saying hypo, you're thinking lower. So we're going to take one more oxygen off. So the formula would be ClO1 and then a 1-. So if you have hypo, you're going to drop another O. Hypo drops another O. All right, you guys tell me the formula for perchlorate. Perchlorate. It's on your sheet. So perchlorate is ClO4 1-, right? Yeah, okay. So we see a little series here now. Hypo meant drop an O. What do you think per means? I don't know. So per means actually like think of like per, like prelude, prologue. So like some of the per stuff means to have more or come before. So we're gonna add an oxygen if you have the prefix per, and that's only for these polyatomic ions. And you'll notice that all of these polyatomic ions, they all have what kind of charges? All of them have what kind of charges? Negative charges, -1, -2, -3. There's only 2, actually really only 1 that we'll use that has a positive charge. Is it on your sheet? You see the one with the positive charge? No, ammonium. Ammonium is NH4, 1 plus. That is the only one that's really a positive charge. You won't see it too frequently though. Okay, we're going to use our sheet for now. Let's go name all the 8s and ites ones. Okay, so, oops, wrong way. Okay, so now we're starting at number 1. Finally, starting at number 1 where you guys have you've been working on. All right, we're still doing ionic. We're still doing the same process. We're taking the symbol and the charge, and the next one, now it will be a polyatomic ion. So I guys have about 7 minutes left with you, so I'm going to make sure I do as many of these as I can. So, everybody, calcium. Shout it out. Ca, charge, positive 2. You are not memorizing these. You have to look at the periodic table. Please don't forget that's a tool. All right, now oxalate. Oh my gosh, we have an 8. It's the first time we've seen it. That means if you see 8, it's a polyatomic ion. You're looking at your sheet. Tell me what oxalate's formula is. C2O4 negative 2. I did not write this down earlier. I'm going to write this down now. If you use a polyatomic ion, you must put it in parentheses. Polyatomic parentheses. Polyatomic parentheses. Write that down for yourself. Because we're going to put in parentheses. Because it's got a, one second, it has a lot going on here in that polyatomic nature. But poly means what? Many atoms. You might start to accidentally put your charge in the wrong place if you don't secure it with parentheses. So if I have a charge out here, and I have a charge over here, when I crisscross it, I'm crisscrossing all the way to the end over here at the back side of the polyatomic. Okay, so I'm going to do that for now to keep you in a good place. After that, we can start to drop the parentheses if it helps. But the 2 drops in, the positive 2 drops out. So then what's your formula? Ca2 parentheses C2O4 parentheses 2. Huh, okay, there's a 2 and there's a 2. I see 2 charges that were 2s. What can I do to make that look better? So I'm reducing it. Okay, so I can reduce this to Ca parentheses C2O4 parentheses. And that's assumed to be a 1 and a 1. We call that calcium oxalate still. This is calcium oxalate, this is calcium oxalate. This is the non-reduced version. Not the best way to write it. We always have to reduce ionics as best we can. But this is what the polyatomic ion oxalate should be, so I'm not touching that. It's exactly the way it should be written. All right, let's do that again. Let's go aluminum permanganate. Aluminum's charge? 3 plus because it's in group? No. Oh, yes, yep, sorry, yes, it's in group 3. I'm thinking ahead. All right, permanganate. 8. Ooh, 8 again. Where am I looking? You're looking on your sheet, okay. Look at permanganate's my favorite one. MnO4 negative what? Assuming negative 1, okay. Permanganate has a negative, does it have a negative 1 on there? Yeah, okay. Just making sure. All right, so making sure I don't make a mistake when I type this. All right, so aluminum, 3 plus, permanganate, 1 minus, crisscross, what do you get? Al, 1, parentheses, MnO4, parentheses, 3. If I did not have my parentheses, what would that last number look like? 43. 43 oxygens? Heck no, right? That's why the parentheses are there to say I have permanganate and I have 3 of them. Not 43 oxygens and 1 Mn. That's 2 totally different scenarios. So you have to put your parentheses. Let's drop to 4. Magnesium cyanide. Magnesium has a +2 charge. You should be quickly finding your symbols now and finding their charges for the first bit, okay? Magnesium is 2 plus charge. Cyanide. Now, I just told you, most of the time ides were from the periodic table. But you'll never find cyanide on the periodic table, ever. It's not there. Look on your sheet for now and tell me what cyanide's formula is. Cn parentheses negative 1, okay? Crisscross, what do you get? Mg parentheses Cn parentheses 2. So you have to put the parentheses on this one as well, because if I didn't, and I'll just demonstrate this for you, just to show you there's a big difference, and that's why the formula is not right if you write it the other way. if you just put MgCN2, how many nitrogens do I have in this formula? 2. How many do I have in this formula? That distributes in 2, okay? How many C's do I have in this formula? It looks to be only 1, but how many do I have in here? 2, because it distributes in. That's why those are different. Those are different formulas if I write them different ways. So I cannot write it this way. I have to put my parentheses. Okay? Just proving to you. Do one more for me. Ooh, this is a mixture one. We have a transition metal with its charge given and hydroxide. So what's cobalt 2? Cobalt with a positive 2 charge, and then hydroxide. That's another one that's a polyatomic, but it fools you because it has the iodine thing. What's hydroxide? OH charge -1. Okay, so here's what you always will want to write. You will see the word hydrox, so hydro, and then oxide, and you will want to write HO, but you will not write HO. You will write O. Okay? Try not to write it the way you see it. Think about what hydroxide should be. Be respectful to hydroxide. All right. So, as we move forward, crisscross your charges. What do you get? CO. What'd you say? Oh, parentheses. Okay. OH, parentheses, 2. Cobalt 2 hydroxide. Okay, I think I probably killed your brains. I'm sorry in this first period. So, what's the next one? So here's what I'll have you guys do. Listen, I don't think you're ready for this. No. You probably need to go ahead and do reading. Start where you can on problem set 9. I'm thinking you can get through halfway through problem set 9. Do not try to name covalents yet. I don't want you to start mixing up your brain, okay? I've already told you it's enough. You have to try to start with problem set 9. All right, take a breather for the last bit. Problem set 9 is under your student packet, under unit 3 still.